Hi everyone, let's do an example of Chebychev's theorem and the 68, 95, 99.7% empirical rule. So let's say that I'm teaching a large lecture hall class of 1,000 students, and all 1,000 scores on a test have been determined. And I find that based on an Excel spreadsheet, I find that the population mean for the 1,000 test scores is 50 points. And the population standard deviation sigma is 10 points. Excel can spit these out for me. Now let's say that the scores between 40 points and 60 points are the C scores on the exam. So I tell the students that if you score between 40 points and 60 points on the exam, then you're getting a C. And only those students are getting a C on that exam. Well, about what proportion of the students, or how many of the 1,000 students would be getting C's on the exam, approximately? Now, the mean is 50 points, the standard deviation is 10 points. So this range from 40 points to 60 points, this interval from 40 points to 60 points, would be all the scores within one standard deviation of the mean. Well, we're asking the question, what proportion of the values are within one standard deviation of the mean? That is, what proportion of the test scores will be between 40 points and 60 points? Chebychev's theorem doesn't tell us anything. We get no information whatsoever. So if I'm unsure what shape the distribution is taking on, Chebychev's theorem doesn't tell me anything. But if I assume an approximately normal bell shape for the data, the empirical rule says that about 68% of the test scores, about 680 out of the 1,000 students, or their test scores, will be within one standard deviation of the mean. That is, between 40 points and 60 points. Now let's say that instead of the interval from 40 points to 60 points, I decide that the C grades are between 30 points and 70 points. So these would be scores within two standard deviations of the mean. So what proportion of the test scores are within two standard deviations of the mean, between 30 and 70 points? Now, Chebychev's theorem says something. Chebychev says at least 3/4, or at least 75% of the test scores, that is, at least 750 of the 1,000 students in the class, score between 30 points and 70 points. Now, it could be more. It could, in principle, be 80%, 90%, 99%. It depends on what shape you're talking about. Again, we could be talking about a variety of possible shapes. Bimodal, this U thing, could be a bell. Now, if we do assume an approximate normal bell shape, the empirical rule says that about 95% of the test scores, about 950 out of the 1,000 students, have scored between 30 and 70 points on the exam. So it's more of a pinpointing. Remember, Chebychev's theorem gives us lower bounds. 3/4, 75%, these are lower bounds. It could be more. I'll do this in blue. So Chebychev's theorem gives us lower bounds. It could be 100%. The empirical rule actually pinpoints an estimate. So finally, let's say that I say that a C is between 20 points and 80 points. Very wide swath there. I think almost everyone should be average. So what proportion of the values are within 3 standard deviations of the mean? That is, between 20 points and 80 points. Chebychev says at least 8/9, or at least 89% of the test scores will be between 20 points and 80 points. It could be everyone, though. If I assume an approximate normal bell shape, about 99.7% will score between 20 points and 80 points. So almost everybody, about 997 out of the 1,000 students, basically about everybody, are scoring between 20% and 80% on the exam. So again, the empirical rule actually pinpoints particular estimates, but that assumes normality. That's a really key, important assumption. Chebychev's theorem applies to a variety of distributions. It's robust or distribution-free, but it only provides lower bounds. And for the score that's within one standard deviation, the lower bound is 0%. There's no information whatsoever. Now notice that the results from the empirical rule are consistent with the results from Chebychev's theorem. So notice that, the 68% is at least 0%, the 95% is at least 75%, and the 99.7% is at least 89%. The empirical rule is consistent with Chebychev's theorem. It does not violate Chebychev's theorem. Remember, we assume these if we have a normal bell shape. We don't assume these for these other weird shapes. Now, you might be asking, well, come on now. If I have all 1,000 test scores, if I have an actual census, can't I just look at the 1,000 test scores on the Excel spreadsheet, maybe sort them, and have Excel count how many scores are between this score and that score? That's true, but let me pose for you the following scenario. Let's say that my teaching assistant, Igor, helps me out on the night of the exam. So these 1,000 students are taking the exam, and none of them cry and go running out. All 1,000 students turn in their exams. Now, after all the exams are turned in, I may ask Igor, so Igor, I'd like to get some estimates going. So why don't you randomly select, say, 7 exams, grade them in the next hour, and report to me what your sample results are. And then based on that, we'll try to estimate what's going on with the class overall. So let's say that Igor takes the 1,000 exams, throws them up in the air, I duck, and Igor randomly grabs 7 exams. He finds that the sample mean is 50 points. And we assume that the sample mean will ultimately reflect the population mean. We'll talk about the inference component later in the course. And let's say that Igor finds that the sample standard deviation S turns out to be 10 points. So again, S is the sample standard deviation. We just had sample data, so we can't get the population mean or population standard deviation yet. So based on the sample, Igor gets from the sample of 7 tests a sample mean, let's say the sample mean is 50 points, and a sample standard deviation. Let's say the sample standard deviation is 10 points. Well, then based on the sample data, based on the sample statistics, I can use Chebychev's theorem and the empirical rule. So let's say that I decide that a C grade will be something between 30 points and 70 points, basically scores within 2 standard deviations of the mean. Then right off the bat, I can say that by Chebychev's theorem, I can estimate that at least 750 of the 1,000 students should be getting between 30 points and 70 points, a C on the exam. I'm assuming that X bar and S will do a good enough job of estimating mu and sigma. But basically, by Chebychev's theorem, I would estimate that at least 75% or at least 750 of the students will be getting C's. If I further assume that the test scores will follow a roughly normal bell shape, I can say that about 95%, about 950 of the 1,000 students will be getting C's in the class. We may be getting a lot of disappointed pre-meds, by the way, if that many students are getting C's on the test. Perhaps it's been the case that in previous semesters, I've seen bell-shaped distributions, so I might feel comfortable in assuming that for now. Or I might just assume that we're going to get a bell shape, and it's just that I want a more precise estimate. I'll go ahead and take this assumption so that I can get this more precise estimate. If I'm not willing to bet on what the shape of the distribution is, I'm stuck with Chebychev's theorem. So based on the sample statistics I get from Igor, I can make predictions about how many C's I'm going to get in the class. By the way, an issue that I could have addressed at the beginning, why are we looking at these particular scores? Well, again, 50 points is the mean. If the standard deviation is 10 points, 60 points is 1 standard deviation above the mean, mu plus 1 sigma. 70 points is 2 standard deviations above the mean, mu plus 2 sigma. By the way, 80 points is 3 standard deviations above the mean, mu plus 3 sigma. 40 points is 1 standard deviation below the mean, mu minus 1 sigma. 30 points is 2 standard deviations below the mean, mu minus 2 sigma. And 20 points is 3 standard deviations below the mean, mu minus 3 sigma. Next up, what would be an interval of usual or typical values? And what kinds of scores would be unusual? Next time.